So today we're going to talk about how do we size bioretention systems for water quality volume. And what we mean by water quality volume is we want to capture the dirtiest water, the first flush that comes off of a site when it rains. And the fact is, when we develop land, almost all the water runs off. In the pre-development condition, we had evapotranspiration, runoff, and infiltration. But once we develop the land, all of those are converted to straight runoff. The difficulty is that if we cannot restore the original evapotranspiration, runoff, and infiltration, which we try to, but at minimum, we need to capture the dirtiest water and hold that on site. There are some great benefits to doing that as well. I'm just going to wait for the dog to stop. So here we have a representation from King County, Washington, of the natural interflow, surface runoff, groundwater for forest condition, and what happens when we develop the land. Ideally, we want to push this as far back as possible because this is what causes flooding. This is what causes stream erosion. All of these have issues of water quality volumes, but the main thing we want to do is we want to try to push back and restore as much of this evapotranspiration and infiltration as we can while we are addressing water quality. So the basic theory behind this, if you look at what happens in a developed area, the natural situation, we would have, it would run up and down. But when we develop land, that hydrograph is going to change. We're going to get to a much higher peak. It actually will peak earlier, to be truthful, and then it'll drop back down. By the regulations that we deal with, we normally have to cut that off using detention systems that we're not going to talk a lot about in detail today, because what we really want to talk about today is this first amount of water, this first flush that we want to capture. We want to capture that on site. We want to treat it, clean it, and then eventually release it. The nice thing about that is that first flush not only represents the evapotranspiration water, but it also represents the dirtiest water. So for most areas, we can capture this water. And if we go down and look at the rainfall on a yearly basis, what this means is that if we can capture, say, 1.5 inches of rainfall, then we are actually capturing 80% of the entire year. And let me explain that again, because it seems a little odd. What happens is that over the course of a year, most of our rainfall is very small. So this is the sort of stuff that happens, every week or maybe every 2 weeks. The big storms that have a lot of intensity, those are very seldom. Those are where we are with the design storms. So previously we have looked at design storms. These are the big storms, but now we're looking at the smaller storms, because if we can capture the majority of those small storms, we are going to be doing two things. Number one, we're going to be capturing the dirtiest water, because the water that runs off the parking lots first is by far the dirtiest water. And we're also going to be helping to restore the ecology of the site, because that same area that represents the dirty water could also be thought of as representing the evapotranspiration that we were talking about previously. So if we capture this water and we capture it in these bioretention systems, we're then going to filter. the water. And there are lots of ways that we can filter the water. Here we just have a set of bioretention systems. I encourage you to come back and look at these later. This one has a perforated pipe underneath. It has a rubber liner to make sure there's no infiltration. But there'll be a good amount of evapotranspiration in this one, and water will be filtered and then allowed to go down the pipe. Here we have another one that again has the rubber liner, and it's simply gathering a different amount of water, detaining it to a level. This is one that does detention, and this one also does infiltration. And then this one here is completely infiltration and evapotranspiration. So I wanted to show you these 4 different ones because what's on the surface doesn't necessarily represent what is underneath. And for all of these, we want to try to capture the water quality volume. We also use the term first flush in the place of water quality volume so that you're aware that these different terms are used. So by controlling that first flush or water quality volume, we need to capture 1 inch to 1.5 inches, depending on the regulations. So we're actually going to focus on 1 inch for this process today. And if we can capture that, the nice thing is it really doesn't take very much area of a parking lot. So in your average parking lot, if you've got a landscape island available, you can easily fit the runoff from a standard parking lot into that landscape island. You can actually think about it as 1/12 the size. So just remember that, 1/12 the size. And that is if we're holding it just say 6 inches deep. I also need you to remember this number at the bottom here, because this is what you can use to convert inches to feet. That's going to be useful to us in this process to convert inches to feet when we're talking about depth. If we go deeper, 12 inches, we can use even less area. The area that we can use for this calculation is just the area on the surface. I love to use the planting soil underneath, but most municipalities will not allow you to count that water because it may have rained a week ago and this may be full of water and soaked in. So it's the surface area above the bioretention system that we're going to be sizing for. So when we design these bioretention systems, we will need to be looking at the total volume of the bioretention system, which is simply the area times the depth. You're not going to worry about that on this exercise, but you will need to worry about it on the next exercise. But for now, we just want you to understand it's the surface area. The area times the depth gives us the volume. This is the sort of thing you learned in elementary school. The other thing you need to be aware of is that we absolutely must break these drainage areas into small systems, small sub areas. And there are a couple of reasons for this. And this is excellent test material. And I don't think we even have it written down in any of the slides. Why would we want to break them into smaller areas? Well, to begin with, it allows us to use more of the landscape area on the site. And by using more of the landscape area, we're able to spread that water out. When we spread it out, we get more evapotranspiration and we get better filtration. So we always want to break it into small drainage areas, and this is what you're going to be doing for your assignment today, actually. Break it into small areas because it allows greater infiltration and a greater evapotranspiration. Many sites you'll work on will not even allow infiltration for legal reasons or other reasons, but they all can allow evapotranspiration. The second reason, of course, is filtering. If we have pipes underneath these systems, such as the drawings that you saw previously, it is much easier to filter the water if we spread it out and run it through more soil. So Greater evapotranspiration, greater filter. Third reason is safety. Many small systems will not be as large or as deep or as dangerous as one large system. So many small systems are safer than a large system. So that's reason number 3. Fourth one is backup or redundancy. If I have one of these systems fail, the other systems are all still working. In fact, they can often take the overflow from the one that's failed. But if I have one large system and it fails, then the whole thing stops working. So the redundancy is the fourth reason. The redundancy allows multiple systems to back one another up. And the last one, of my favorite, and I'm not even sure this goes in any text or test, but I love it anyway. More landscape areas create more planting areas, and I like planting areas. And the more planting areas we get to play with as landscape architects, the more fun I'm having anyway. So those are some of the reasons we need to break it into small areas. But the number one reason, again, is the hydrology. If we break it into small areas, it's much easier to treat the water than if we have it all in one large area. And so this is an example of what we're talking about. This is the assignment that you're going to be working on. These are examples from previous students. And we're going to take your hard surfaces, your parking lots, your plazas, your roadways, and we're going to subdivide those into smaller areas, preferably between 1,000 and 5,000 square feet. We're then going to take those areas, and at the end of them, we're just going to draw rectangles. These are not bioretention systems. This is a mathematical proof that you can make it work. That's all it is. So if you're looking at this drawing here, we're going to say that area L drains into the rectangle L. Area K drains into the rectangle K. Area Q drains in the rectangle Q, but it's a little hard to see. And by the way, these examples are not all correct. So I'm going to stick over here on the parking lot where it is correct. And so this is what you're going to be doing. And I'm going to pop over to your actual assignment real quick to talk about this. Your assignment in week 7 says that you're going to break these parking areas down into sub-drainage areas. You're going to color code them. You're going to calculate how much runoff depth is going to be generated. And we're going to talk about that in a minute. And you have different runoff depths from impervious surface, like parking and walkways. And then for pervious surfaces such as porous concrete, you have a 1/2 inch. And then for green roofs, you have a 1/2 inch. You're going to color code those to match them with the drainage areas, and you're going to show the capacity of it to hold that water. So these are the steps that you're going to go through, and we're not going to go through them all with you right now. Note that the conversion is here, but we'll go through them. First, you're going to delineate your proposed surface as impervious, pervious, or green. Then you're going to divide them into smaller sub-drainage areas. That is probably the most difficult part of this assignment, dividing them into the small subsurface areas. So I'm going to show you an example. Here we have someone's AutoCAD drawing from a year or more ago. It's just one I randomly gathered. I told you a minute ago that your areas that you're going to capture are going to be areas between 1,000 and 5,000 square feet. And on this drawing, I actually created some rectangles. My rectangles happen to be 20 feet by 50 feet. You know, each of these rectangles is 1,000 square feet. So 5 of them is 5,000 square feet. And so you can look at this and say, oh, okay, well, you know, if I'm going to do something on here, you know, let's just say, well, that looks like, you know, something that might fit. That might be about the right size. It might be a little smaller, might be a little larger, but it looks like it's bigger than 1,000 and smaller than 5,000. So that's exactly what you're going to be doing, but I'm going to try to show it to you with a little more. I'm just trying to make it a little easier for you. So the first thing I'm going to go do is I'm going to set up a P line like I just did. And when I set up my P line, I set it up with the width of 1 foot, so it sticks out on the screen very easily. That's something I'm not going to go over right now, but I am going to go down to my snaps. And I'm going to open up my snaps, and I look at all these snaps that are here. And you guys tend to get a lot of snaps. I'm going to turn off everything and then turn on perpendicular. And I'm going to explain why in just a minute. The hardest part that students have with this assignment is going perpendicular to the contours. So if we go back and look at this, you can see we are running perpendicular, not parallel, but perpendicular to the contours. Somebody will start this project and they'll say, oh, I'm going to get, you know, this area here. And that is dead wrong. Dead wrong. Instead, you want to be going perpendicular to the contours. So one of the things that makes that easy, if I go back to AutoCAD, is right now the only snap I have is perpendicular. Because the only thing I'm going to snap on is contours to get a rough idea here. And so we're going to go back to this little corner that we had, and we're going to start our P line. And I don't know, I'm just going to pick right there. I did get a perpendicular, I don't care about that. The perpendicular I want is right there on that contour. And then the next one I want is on that contour. And then I'm going to turn my O-snaps off as I finish this. Now, there are two ways to turn the O-snap off. One is to go over here and turn it off. And the other, you may note, is, and it tells you right there, the F3 key. So if you have a keyboard that has an F3 key, you'll use it a lot. And most of your keyboards have an F3 key. Sometimes you have to put the function key down at the same time. So I'm just rolling along here, and I'm going to hit F3, which turns my snaps off. Again, let's go over here and look at it in the corner. You can see on, off, and all I'm doing is hitting the F3 key. And then I'm going to eyeball straight up, and this is all I'm doing. I'm eyeballing, and I'm tracing. I am not snapping. I am not using O-snaps because I really don't care. It doesn't have to be that accurate. And we get close to where I'm at the end. I hit the C for close. That is to close a P line. You simply hit the C on the keyboard and hit enter, and it's now closed. How big is that thing? I can simply type LI, list, click on it, and it tells me that this is the area. That's about 3,000 square feet. And that is perfectly acceptable for the size we want to use here. About 3,000. Great. We'll leave that one. Let's do another one. P line. I'm just going to pick somewhere around here. I'm going to turn my snaps back on so I can go perpendicular. And I'm going to turn it off as I come up to the edge. And I'm going to roughly come down, close it, list it, get the listing. That one's up at 4,000 square feet. That one's still acceptable, agreed? And this is exactly how we do it. We can make them larger or smaller, but this is basically the idea. And I'm going to continue this for a little bit because I want to show you what happens when we, and here's my perpendicular, when we get to, say, a ridge or something. So here I'm just coming around, bringing it back, closing it, doing a list on it, even though I already know that one's fine just by eyeball. That one is 3,777. That's nice. And we'll go down another one. This one I might make a little smaller because I'm going to come up into this driving area. And I don't want to get over 5,000 square feet. But I want you to notice there's a ridge line right here. And that ridge line is important because water is going to go different directions at that ridge line. So now for my P line, I'm just going to, I'm going to make it a little narrower. Nah, I'm not. Let's try it here. Use my perpendicular to go up. And then I have to eyeball up to that ridge line. Notice I turned my F3 off. So now I'm going to loop around, go in this way, down, close it, do a list on it, take the listing, 3,500 square feet, perfectly acceptable. The thing that was important to note there is that this ridge line is a divider. So when I get to that ridge line, I have to stop and go, because the water on this side goes the other direction. There is no reason for the ones on this side, the drive side, to line up with any of the corners that you have here. So what you do in all honesty is, again, on the other side, we're just going to pick a point. And eventually you'll understand how this works in terms of estimates. Oh, I'll just go down there. And I'm going to go perpendicular, turn my perpendicular off, go all the way up. I actually have to go along the ridge line. Close, list. That one is 2,800 square feet. So you get a feel for how we do this. Things get complicated when you get down into the valleys. And the reason is that in the valleys, areas get rather large. So I'm just going to try one right down here for the fun of it and see if I can actually get it within the 5,000 square feet. And I bet I cannot. I'm starting from that very tip. And I'm going to go up like this, over to here. Oh, look, what did I just do, guys? What's the mistake I just made? I crossed the ridge line. Absolutely. Bad boy. So let's get rid of that guy. Do it again. Start down here. Now I have to stop at the ridge line. Now this is going to go all the way over to here. Oh my heavens. In fact, I'm going to stop there because I'm not quite sure where it's going to go. And I'm going to start down at the bottom again. I'm going to start down here again. And I'm going to go up perpendicular. Wow, that's a lot of area. So that's a rough outline. I'm now going to come back and put a P line over top of all of that so that I can get the entire area. You notice I don't waste my time even trying to join the P lines. So now that P line is a separate entity, and you can see I can grab it and move it around just like that. And I can go back and delete the old stuff. And then I can move this one back. And my guess is we're going to have a problem with this one. It's going to be too big. So let's do a list. We are too big. We are at 6,757. So what do we do? What we do is we subdivide the area right now and say, you know what? I've got a couple of ways that I could subdivide this. And I'm going to show you two of them. So let's remember, we're going to do two of them. The first one is I might say to myself, you know, I'm going to add a bioretention area right in the middle of this. And I'm going to move it up to right to that edge because I can. So if that's a bioretention area, I'm now going to play with what water would drain into just it. So because water drains perpendicular to the contours, I can go up to there, over to there. I'm not sure how far I'm going to go over here, so I'm just going to stop. And now I'm going to start my P line again on this edge, up to there, up to here. Now, you might be saying, why did you start it on that edge, Stuart? Because I tried to pick the edge that was, frankly, tangent to the line that's going straight uphill. To make that a little more clear of what I'm trying to do, I'm trying to get all the water that drains that direction captured in that bioretention area. So I'm subdividing it. I'm now going to do another P line to run around all of that. Helps to get back into AutoCAD, of course. So here you see my new P line running around. I'm just copying what was there before, closing it. That's cool. I'm now going to move it out of the way for a moment so that I can get rid of the old ones that I don't need anymore. I'm now just going to move it back in place because I like it over there. And so now I can look at the area of this one. And that is now 2,800 square feet. That is acceptable. In fact, if I roll all the way up and find the one that we had way up above, and I'm too lazy to do that, we could just do the subtraction. But instead, I'm going to do another P line. And it's going to run over top of all of these things. This is the P line of the water that does not run into that little bioretention system. And again, I'm going to move it out of the way so that I can see what's going on here. I'm going to eliminate that, and then I'm going to move it back. And what is the area of this one? The area of this one is an acceptable area. So I've now divided that area that was too large into two separate areas. And by the way, when you get into doing your hatch work, that P line can still work for your hatch. So if I wanted to hatch something and I have to pick an object, I can say that object there. And I don't know if I selected a hatch. No, I didn't, but you get the idea. Yes, I did. So there you can see my hatch in a lovely black. Let's cheat on the color. So that's the area for one of them. And if I wanted to do a hatch for another one, I could do that by again selecting the area. So that's now a hatch, and I take that and I'm going to change its color to something else. So there you can see I'm even starting my coloring system. So let's get rid of all of this. That was one way to divide it. The other way to divide it is to add trench drains. And a trench drain, I think there's actually an example in your resources, but we'll look at one again in a little bit. A trench drain simply allows me, a trench drain is simply a drain that is in the ground on the pavement. And so, for example, I could create a trench drain right there. And what would happen with that trench drain is that the water that is coming down this way will be captured by that trench drain and then sent off to the side. So what that means is I could then come in with another P line and I could say, all right, I'm going to take from that trench drain, turn my snap back on so I get perpendicular, only up to the ridge line, thank you. Over this way, this way, this way. And over here, I could bring it all the way down along here. The idea being that the water that is over here is going to drain into that same area anyway. And then I can do a list on that P line. And the area of that one is 4,200. So that one is acceptable size. So there are two ways to subdivide these larger areas. One is that you can create a bioretention area in the center of it. And the other is that you can add trench drains. But to begin with, what you really need to do is you really need to work with getting these areas subdivided. So all of these areas have to be subdivided. And I wanted to show you an example. And my advice is start with the easy areas out here. Start with the easy stuff. Learn on the easy stuff. Learn to avoid crossing the ridge line. And then life gets more complicated where you have these swales, and you'll do those second. So I want to go back to the assignment. So calculate the square footage of each of the drainage areas, record it in a spreadsheet, an Excel spreadsheet. Multiply the square footage of the drainage area of each surface. Note that you're trying to get the 1-inch depth. And to do that, you simply take the area in square feet and multiply it by 0.083, and that will give you the water quality volume. And that's the key thing that we want. We want the water quality volume. So if I go now and look at this sheet, that's fine, but the next sheet shows you what's going on. We have drainage area, and that actually, by the way, is over here on the side. So we have drainage area A. Here's the total square feet. This is the depth. And this is the total cubic feet that we want to hold. Most of these, the depth, by the way, is the depth of the bioretention area. We can go down and look at another one of these, and it gives you a better way to look at it. Here we have area P1. Runoff depth is 1 inch. This is the area. This is the area that's going into the bioretention. This is the depth of the bioretention area. It's always nice to keep them 6 inches or less. And this is the volume that the bioretention area holds. That volume was determined by taking this number and multiplying it by 0.083, and that then gives you the volume that has to fit into the area. So if we look at these, we call it the Rainbow Project because we think it's really kind of fun to have all these different colors, and besides, without the colors, you will never be able to figure it out. And just to make sure you know this is not current practice in landscape architecture, except in a very few highly sophisticated firms. This is future practice for landscape architecture, breaking everything down into the individual water quality volumes and distributing that water throughout the site in order to manage it in small distributed systems. These are the basic instructions of what you're going to be doing, which are simply copied from the assignment. These are the suggested steps that you go through. And note, this is a mathematical proof that you can fit the retention on site. This is not retention design. This is just the mathematical proof that you can fit it in. So when you look at one of these drawings, this is not necessarily where they're going to put their bioretention in terms of shape and placement. These are just rectangles to show that it will fit. And what's actually rather amazing, if you look at this, is that it doesn't take a whole lot of area to fit these in. So anytime you're dealing with folks that say, we don't have room on the site to do bioretention, you can see that it's not a problem at all. Question from Adam, how do we know what depth it should be? It's up to you. And we would like it to be no more than 12 inches deep. So actually, I could go back to the assignment to make that easier to highlight. Depth of 12 inches. Note, you may combine systems only if needed. And of course, note, it's only a mathematical proof. These are not actual designs. Follow the rubric to determine what's needed for your records. Frankly, the examples we have shown you are pretty good.